So, what benefit does digital modulation bring us? It should be obvious by now. Greater channel capacity. Channel capacity is dependent on the number of bits represented by each symbol or location on the IQ diagram. For the same amount of bandwidth, how many times more efficient is the 16 QAM modulation scheme compared to a BPSK modulation scheme? The answer is 4 times, because the bit rate of 16 QAM is 4 times that of BPSK. This is why newer dial-up modems have higher bit rate such as 56K bits per second as compared to many years ago, when the typical bit rate was just 2.4K or 9.6K bits per second, whereas the phone line bandwidth has remained fixed at just 4 kHz. But there is a trade-off in packing in greater channel capacity into the same bandwidth. The areas shaded in gray show the allowable deviation in the symbol location for BPSK and 16 QAM. BPSK has much greater allowable deviation than 16 QAM before a symbol crosses over to another symbol's location, which would result in symbol error and hence bit error. So the trade-off for higher channel capacity is a lower tolerance to nonlinearity, distortions, and noise. These modulation schemes are used in different applications according to the channel capacity and error tolerance needed. Example, BPSK is used for deep space telemetry and cable modems, while 16 QAM for digital terrestrial television in the UK. An IQ modulator is used to perform digital modulation at the transmitter end of a communications link. The incoming I and Q signals must first be band limited using low-pass filters to limit the frequency spreading caused by the modulation. The baseband signal is then up-converted using mixers. The Q signal's carrier is 90 degrees phase shifted relative to the I signal's carrier. The two signals are then summed to give the total modulated signal S, which is the sum of an ASK modulated sine with an ASK modulated cosine signal. The resultant signal is a sine wave with both amplitude and phase modulation, with amplitude and phase depending on I and Q. The advantage of this method is that the two ASK modulated bit streams can be scalar. This simplifies the design of digital radios and can support complex modulation schemes such as 16 QAM without the need for a phase modulator. At the receiver end, the signal is demodulated by an IQ demodulator to extract out the I and Q components which are orthogonal to each other. The received signal S is split into two paths, one going to the I component and the other going to the Q component. They are multiplied with a local oscillator clock that is recovered from the received signal. The recovery of the local carrier must be accurate in frequency and phase, otherwise it will result in symbol and bit errors. The I component is multiplied with the local carrier, while the Q component is multiplied with a 90 degrees phase shifted carrier. The signals are then put through low-pass filters to recover the I and Q signals. Let's take a closer look at how this works. Let's look at how the I component is obtained. The received signal S, which is made up of I and Q, is mixed with the recovered carrier to give a difference term, which is at baseband, and a sum term at twice the carrier frequency. The plot shows two carrier peaks, one at DC and another at 2 omega. The Q component is processed in the same way, giving peaks at DC and twice the carrier frequency as well. The final step to obtain the I and Q components is to put the signals through a low-pass filter to remove the high-frequency component, leaving just the baseband component which contains the I and Q signals. The I and Q can then be converted to digital bits, and the desired information can be recovered. Earlier, we had learned about several important reasons for modulation, which is to upconvert the signal to fit into a suitable antenna size and percentage bandwidth, and to enable multiplexing. Hence, to complete our transceiver chain in a communications link, an RF transmitter and receiver needs to be added to our system. The RF heterodyne transmitter upconverts the intermediate frequency, or IF, from the IQ modulator to an RF signal suitable for wireless transmission. Similarly, the RF receiver side downconverts the received RF signal to IF. The heterodyne architecture enables the rejection of unwanted interferers. For example, the first bandpass filter at the RF receiver is to reject image frequencies, while the second one after the mixer is for channel selection and to reject adjacent channel interferers. There is a trade-off between image rejection and adjacent channel rejection, and to achieve a more favorable trade-off, architectures with two IF frequencies are used. More recently, a new type of receiver has come into focus due to market pressures on costs, power consumption, and form factors, and also the availability of new IC technologies. This is called the Zero IF or Direct Conversion Architecture, because the IF is in fact at DC, and the RF is converted directly into baseband without the need for an IF stage. So, what is this new architecture? It is simply our standard IQ demodulator. In fact, direct conversion radio is not a new idea, but an old one invented decades ago. It has not been popular in the past due to the difficulty of implementing it successfully using discrete devices. Monolithic IC technologies, on the other hand, are more likely to overcome the challenges of direct conversion radio, hence the resurgence of interest in it. Well, isn't it true that sometimes a great idea is just too far ahead of its time?